All right, so this is lecture 14, and we're going to be talking about where do gauge theories come from. This is a lecture stolen from part 1 of QFT. It was supposed to be QFT 1, but now we're covering it. Hopefully, we'll have time to wrap it up in one lecture because I'm planning on describing the origin of gauge theories, some geometric picture of gauge theory, and give you a lattice picture if we have time. Hopefully, we'll cover all of that. All right, so we said that gauge transform, if there are any questions, I'm reviewing lecture 13. If there are any questions, please do ask. Gauge transformations are redundancies that we introduce to obtain a local action. So the theory we're going to see today that these gauge theories that we're talking about, these have inherently non-local operators called Wilson loops or Wilson lines. Wilson loops is perhaps a better way of saying it. And if we have to we introduce, because we insist on a purely local description, we achieve that by introducing some unphysical degrees of freedom called gauge degrees of freedom. And the example is electromagnetism. Photon is spin 1, it's massless. There is no local action you can write down for a massless spin 1 particle with only 2 polarizations, because spin 1 particle, the action you write down for it, it has automatically 3 degrees of freedom, which are but the longitudinal degree of freedom we do know is unphysical. All right, so gauge transformations can be viewed as local transformations that keep the action invariant. So this is to be taken with this is like to be understood as not an actual transformations in the Hilbert space, but it's in this unphysical enlarged Hilbert space, right? Not the physical one. All right, so what you're dealing with is, imagine you have some sort of a particle. It could be it's a charged particle, and it's a say On or Un. It's a vector. Say it's a fundamental representation of some group. Then what we're going to do is that we're going to apply a transformation, quote unquote symmetry. It's not a symmetry transformation, it's a gauge transformation that depends on the location in space, right? And we're representing it with a matrix. Then the first issue that comes up is that del mu, the kinetic term, the conventional kinetic term, is not invariant. The reason is that the derivatives will act on the position-dependent transformations, and that will give you extra terms. We said that a way to fix this is to upgrade this to what we call the covariant derivative. And that is how the story of gauge theory goes. So for instance, to start very simple, let's start with the abelian gauge theory first, or actually, no, sorry, not necessarily abelian. Take phi to be a complex field that's in the fundamental representation of Un, right? So there are these n by n complex unitary matrices that acts on phi, position dependent in a position dependent way, and these are gauge transformations. What is a covariant derivative? The covariant derivative is del mu. Now, del mu acts on a vector. So this is identity. It's an n by n matrix, right? So this covariant derivative is a matrix valued minus Ig a mu of x. This is also matrix that depends on x. And the idea for introduce this new matrix valued field, because if we do so, then if we require that it transforms this way under the transformation of u, then we get a cancellation. Then what we get is that d mu transforms covariantly. So the effect of this, if a mu, the gauge field, transforms this way under the transformations, which is adjoint, right? So u fundamental left, u dagger from the anti-fundamental the right, and then this extra bit, if it transforms this way, then the covariant derivative transforms this way, right? And now it's pretty obvious that d mu phi is invariant, right? So now the covariant derivative just transforms nicely. as a matrix, it transforms in the adjoint representation. This is precisely why we introduce a gauge field. This is the raison d'etre of the gauge field. All right. So an example is helpful. Take the case of SU2 gauge theory. Then everything is, so your field is so your charge matter is complex two-dimensional vectors, right? And now you have a Lie algebra that we represent by half of Pauli matrices. So your gauge field is Pauli matrix valued, 2x2 complex matrix valued fields like this, right? This is your gauge field. And here I have to tell you that in these notes, in various places, I will use this as the generator of the Lie algebra. Sometimes I use this as the generator of the Lie algebra. At any rate, these are all matrices, right? Sometimes I put this, sometimes I don't, right? Okay. So as I said, this is a matrix valued, but now this K, just keep track of this. This K is the, so these are the matrix indices. A and B run from 1 and 2 in SU2. K runs over what? X, Y, Z, 1, 2, 3 of sigma Pauli's, right? So this runs from 1 to 3, which is the dimensionality of G, right? SU2 is three-dimensional. And then the components of A mu for non-abelian gauge theory, of course, there's A mu, which is mu of space-time, but then they're labeled by K, generators of SU2. Okay, good. Now, under an infinitesimal transformation, UAB, which is a SU2 group element, we saw this in QFT1, we linearize it around identity, right? An infinitesimal gauge transformation is going to be identity plus I theta of K, now it's X dependent, times the generator matrix. Repeated indices are summed over. K is summed over, right? Similarly, del phi of A transforms this way. It's one-liner to derive. And then the gauge field transforms this way. Now, what is interesting is that the gauge field transforms in the adjoint. So in the adjoint representation, lambda of LKM, these matrices are nothing but the structure constants. Sometimes I write them as F, sometimes I write them as C. Depends where I stole the notation from. All right. Any questions? Now, what is the field strength in U1 gauge theory? So field strength in U1 gauge theory, electrodynamics, was just the matrix of F mu nu, right? F mu nu of X was del mu of A mu of X minus del mu of A mu of X. What is this matrix? Well, it's clearly antisymmetric. It's 4 by 4, right? There is the electric field, EX, EY, EZ. That's antisymmetric, right? And then here, I'm going to get this wrong. BX, BY, BZ with the right components, right? So these are the physical degrees of freedom. All right. These are the physical degrees of freedom, right? And they're all gauge invariant. The physics of the physical degrees of freedom of the electrodynamics is in here. We're going to see that this is not all that there is to electrodynamics. There are non-local degrees of freedom. These are obviously local, but there are non-local degrees of freedom, and that's why we have to do that. That's why it's a gauge theory. Now, let's see how this idea of F mu nu comes about and how we're going to generalize it to define field strength for for non-abelian gauge theory. So a nice way of writing F mu nu is as 1 over minus IE is electric charge, the commutator of d mu and d nu. These are covariant derivatives. So let's see why that's the case. Well, here, what is d mu? D mu is del mu minus IE A mu, right? the commutator of these two will come from a mu acting on this guy, and well, that's basically where it comes from, because these two guys will commute. These guys will commute. These are just like 1-by-1 matrices. These are functions, right? So the commutation relations come from the fact that del mu can act on a nu. So once you expand this, you're gonna find that this is minus IE del mu a nu minus del mu a mu acting on phi. Right? Now this is what we call field strength, right? So it's natural to define F mu nu as 1 over minus IE, the commutator of the covariant derivative. Is this calculation clear? There's a very nice geometric picture for this that I'm gonna explain in a bit. At the moment, this is just a derivation, right? It's just algebra. All right. Now, let's try to define the non-abelian field strength the same way. So it's minus 1 over IG. G is the coupling of the non-abelian gauge theory, the commutator of the covariant derivatives, which are now matrices, right? These are an important thing to keep in mind is that F mu nu is now a matrix valued field strength. Good. A particular component, space-time component of F mu nu is just a field for electrodynamics. For non-abelian gauge theory, a particular space-time component of F mu nu will be a matrix valued field, right? All right, so let's do this. Well, you could just expand. This is pretty straightforward to see how. Oh, let's first see how it transforms under gauge transformation. Well, under gauge transformation, the covariant derivative transforms like u dagger, as we saw by definition, by construction, it was transforming that way. So here, oops. So here's how they transform. You can take the u and u dagger out of the covariant derivative. So you find that, so as matrices, they transform covariantly in the adjoint. F mu nu transforms in the adjoint. So what does that mean? It means that it's not gauge invariant. So F mu nu for non-abelian gauge theories, I cannot stress this enough, is not a physical observable. This is a big distinction between non-abelian gauge theory and electrodynamics. In electrodynamics, F mu nu packages for you in a tensor, in an antisymmetric tensor, your sum of the physical degrees of freedom you have, the local physical degrees of freedom you have. But I said the word physical, therefore they must be gauge invariant. However, the non-abelian field strength is not gauge invariant. It transforms in the adjoint, right? Now, what was the action of U1 gauge theory, electrodynamics? The action of the U1 gauge theory was this. This was the action. Lagrangian density. Do you remember y minus 4? No. What we usually put for scalar, we put half. Why do I put 4? What is this? This is del mu n mu, del mu, oops, sorry, minus del mu n mu times the other one. When you expand this, you get 4 terms. 2 of them have the form you want that look like a scalar. That's why I put 4. All right, any questions? So suggest an action for a gauge invariant Lagrangian density for non-abelian gauge theory. Come on with a suggestion.
You would have to introduce the commutator of the non-abelian gauge field.
Field strength?
No, of the field, of the So that field strength is still, I mean, that field strength should have the commutator of the A's.
So the field strength, so yeah, field strength does have the commutator as defined to be field strength, definition of field strength. Yes. This is the very definition of field strength.
Yes, but then those D's are 1 times del mu plus the
So
then
yeah.
yeah.
So what is the action I write down? Give me a suggestion. So F mu nu, if I want to build it out of F mu nu, this transforms as an adjoint. I don't want to build it out of A mu's. Is that clear? That should be clear because they transform, their transformations are wacky, right? They don't transform covariantly. There's this extra derivative. They're unphysical for one thing that's obvious. They're unphysical. So this guy has a hard. This is still not physical, but transforms in a nicer way, right? So how does it transform? It transforms this way, right? So if I write this F mu nu, how does it transform?
Same.
Good. So if I write F mu nu, it transforms like this. This is a matrix, right? Is there any suggestions? Is there any way I could turn this into something invariant? Trace. You don't want a matrix in your Lagrangian, right? You want Lagrangian density. So take the trace, and you're done. Now here, you could have written this. Why didn't you write this? This is gauge invariant, right? What's the problem with this? It's not Lorentz invariant. So you need at least a pair of these guys. Good. So here's the action. Oh, all right. So I'm just telling you in advance what the action is. It's called the Yang-Mills theory. So the Yang-Mills theory, the action of the Yang-Mills theory is minus 1/4 T of R, that I'm going to define a bit. Trace of R, F mu nu. So you know that these are matrices, right? These guys are matrices, so they're in a representation. Good. This is all done in representation R. So this trace is in that representation R, and this will, what I divide by depends on the representation. And we're going to spend some time deriving what this is. But this is called Yang-Mills theory. If you integrate this is called Yang-Mills theory. Yang-Mills theory is electrodynamics. Electrodynamics is a free theory. That's clear, right? However, Yang-Mills, non-abelian Yang-Mills is not free, it's interacting. Is that clear? We'll can you see it already?
Interaction.
Where does the self-interaction? There's self-interaction. Where does it come from?
From the non-commuting property.
How do I see that?
You expand the mu nu in terms of the.
Very good. So let's do that. All right. So F mu nu schematically looks like this. Well, it's this. It's d mu. Let me. I have a slide about this. I'll show it on the slide. Can you see it though already? Where does the what's going to be the field that you're saying interaction versus not? What's the field? A. Good. So is the kinetic term we wrote the kinetic term? Is this second order in? So we call it kinetic term if it's second order in A mu, right? And it's also second derivative. Is this second order and second derivative in A mu? Is this term? It is. This term it is, right? But it has a term which is second order and second derivative in A mu. Not the whole thing. Why is that? Can you see that? Each F mu has terms that look like d mu. each d mu has one copy of a mu a mu, right? Well, there are the derivative piece, and then there is this. So when you expand this, you're going to get a standard two derivative, two a terms. You're going to get a term with one derivative, three a's, and you're going to get a term with four a's. So if you were to guess the Feynman diagrams for this, representing this with wiggly lines, this would be, from expansion of this, there will be a propagator. There would be something that looks like this, and it has a derivative. There's a momentum in there. And then there will be this, and that's it. Now, notice that the fact that this, we try to write down, there is no way of writing something down, which is non-interacting, and simpler than this, and it's gauge invariant. There's no gauge invariant, non-interacting things you can write down. This is the simplest thing you can write down. It's a good challenge. Play around with it. This is the simplest local thing you can write down. And it comes with these derivatives. So I want to point out that previously we saw in non-abelian, in linear sigma models, non-linear sigma models, we saw that the principle of symmetry was sort of protecting the theory and the format of the interaction. The interaction had to take a very particular form because of the symmetry, right? Here, the gauge invariance is the principle, right? The gauge invariance requires your terms to be like this, right? So these are not two separate interactions. They're locked in together with one coupling. There is a G here, right? The G is in, I put it in F mu. Good. All right, is the Yang-Mills theory. So Yang-Mills theory, non-abelian Yang-Mills is immediately an interacting theory if it exists. And we'll see that it will exist. All right. Now I'm going to immediately change the notation. Sorry about that. So quadratic Casimir. So I'm after telling you what this T of R is. A little bit of a very quick reminder of the discussion of Lie groups and Lie algebras from QFT1. If you have a representation R of a Lie algebra, in a representation R of a Lie algebra, we're representing every generator with a matrix. A runs from 1 to the dimensionality of the group. And this is the Lie algebra and the Lie group are connected via exponentiation, right? So an element of the Lie group is exponential of this repeated indices are summed over. Just a little bit earlier, I called this theta and called this lambda. Lambda k theta k, a couple of slides before. So when you expand this, you're going to get something like this. The commutator of the Lie algebra generators satisfy the following relations. These are the structure constants. Good. Furthermore, Lie algebra satisfies the following identities called Jacobi identity. So what is a Lie algebra? It's a vector space, right? With a bunch of vectors generated by a bunch of these TA is are bases of that vector space. So you could sum TAs as we were doing with a bunch of coefficients. This vector space has an operation which is a commutator. We're just writing it this way. This is a form, and it satisfies these relations that FABC are a bunch of symmetric properties. And then finally, it should satisfy a Jacobi identity. Such a thing is called Lie algebra. Now, why are we requiring Jacobi identity? Oops. Why do I insist on Jacobi identity? What's the physics of it? Well, it's staring at this. You might wonder why the hell would you ever consider such a thing?
It's like the order in which you apply the things. If you apply them in that order, they don't do anything.
No, in this order. So there's a reason for this. Okay, I'm not gonna give you the grand math answer because I don't understand the grand answer. But as a physicist, I'll tell you this. This is Lie algebra, and you wanted to have a representation. Representation means that every TA, TB, TC is going to be a matrix. For any three matrices, A, B, C, this is a fact. Matrix multiplications. And if you define A and B as AB minus BA, as we would like for representations of Lie algebra, this is just a fact about matrix multiplication. So if you're defining abstractly a Lie algebra, you better satisfy this property, right? Because, yeah. Good?
I don't understand how it's a vector space, because are vector spaces equipped with operations that take two vectors and return a vector?
Yes.
That are in addition?
We'll write this down. These
But
are vectors.
Matrices you can multiply.
Mhm.
But vectors you have addition. You only have addition. Like you can add two matrices together, but you can also multiply them.
Okay. All right. So just some a little bit of linear algebra. So what is vector? As you're saying, a linear vector space, right? The elements of linear vector space are vectors, and you have addition operation, right? And it might be complete or not. You might have a norm or not, right? What is an algebra? An algebra is a linear vector space where addition is addition, and then there's multiplication. So an algebra is also a linear vector space.
You have to include it.
Yeah, you can add matrices. And matrices with respect to the addition operation is a vector, form a linear vector space, right? We're talking about the Lie algebra. So the moment we say an algebra, it means that there is a notion of, it is a linear vector space. What is important here is that the Lie algebra, as opposed to the algebra, so I don't want to say this, but abstractly speaking, I'm just giving you some intuition. Abstractly speaking, what is multiplication? It takes as input two elements of the linear vector space and pops out another element. This commutation relation does something like that, abstractly speaking. Abstractly speaking, you don't need to define TA times TB, right? Okay. Of course, via BCH, this is what controls the multiplication of group elements, right? That's why this is defined this way. All right. Any other questions? Now, the same way that, oh, by the way, if there was a homework in QFT1 about this. No, not in quantum mechanics. There was a homework about this. The set of matrices form actually complete Hilbert vector space Hilbert space as well with an inner product. One choice of inner product is this. So you can think of it this way. Right? So this is a vector, this is the conjugate vector, this is a cat, this is a bra, and this is their inner product. Right? So in that sense, when I talk about TATB, so when I write this equation, there is one question that comes up. As a vector space, is there an inner product? The inner product, this is like multiplication, takes 2 as input, pops out, it's not quite multiplication, but spits out another object. Inner product would have to take as input TA and TB and pop out number, what comes to mind?
The determinant, the trace.
Trace. Certainly sounds fancy, right? So if this is to be interpreted as inner product, you would like to choose your generators to be orthogonal. So you would like this to be proportional to delta AB, right? Let's call the coefficient of that T of R. Right? Now, is this something that's decided by the algebra, or do I have a freedom to rescale these vectors?
You have freedom to rescale.
Sorry?
You have the freedom to rescale that.
What happens if I rescale them? Can I get rid of T of R? Jacobi identity is fine, because every term is multiplied by a constant, so a cube. But what goes wrong? This goes wrong. Right? Structure constants are fixed. It's not up to you to rescale it. That is why this is something we can calculate for Lie algebra or Lie group. If we could arbitrarily rescale it, and then this I didn't need to. There was no meaning associated with that, right? All right. So here's what it is. So TATB trace of R. There's T of R. Here's the notation. T of R of A means the generator, eighth generator of this group in representation R. So for instance, I apologize about this notation, it's pretty standard. T of A of G, G means adjoint representation. It's not G of the group. When people put G next to a generator, they mean the adjoint. This is an adjoint representation. When they put N, they mean fundamental. And when they put N bar, they mean anti-fundamental. At least physics C term, literature. Mathematicians probably have something completely different. So now, based on what I told you, what is T of R? This is also sometimes called C of R, by the way. What is T of R for the fundamental representation of SU2? So what are the matrix elements of SU2 for the fundamental representation? They're half Pauli's. So you would have to put sigma x. What happens here if I put this? To half. You can compute it as half, right? Because half Pauli's is square to identity. This guy, square of it, is quarter identity. Trace of identity is 2. That kills 2 of them, we get half. Right? So for SU2, what do we say? We say that T of A of, this is really confusing, so it'd just be maximally confusing. T of A of 2 is, oh, sorry, half. What does this mean? It means that, oh, no, my bad. That what I'd written was actually correct. So here what I wanted to write is T of 2 is half. T of N in the fundamental representation, when this R is N for SU2 is 2, right? T of 2 is half. This is really a shorthand notation if all the groups you work with are just SUN and nothing else really, right? That's basically our story for this course. Good. So is T of R clear? Now, when you learn about representation theory of SU2 in your quantum mechanics course, how did you do representation theory of SU2? Say Pauli's, well, fundamental representation. How do you label SU2 representations?
Like you start with half integers.
What are the quantum numbers of SU2?
Spin.
What are the quantum numbers of SU? An irreducible representation of SU2 is labeled by how many parameters?
LS.
well, we usually call them J and M. Or L and J and M usually for SU2, for SO we usually write L and M, right? Maybe we write J and S. I don't know. Anyway. Now, what are these numbers? What are the values they can take for ERAPs of SU2? 0, half, 1, 3/4, for SU2. And M runs from, M is an integer, half integer, sorry. And it runs from minus J to J. So this ERAP is 2J plus 1 dimensional, right? Now, you know what this guy is. These are the eigenvalues of sigma Z. What is J an eigenvalue of? J squared. What is J squared? X squared plus JY squared plus JC squared, right? So for us, this guy looks like TA sum over A, right? What is the property of J squared? It commutes with everyone. This guy, check explicitly. In any representation, TA of R squared sum over A, this is called the quadratic Casimir, and you could check explicitly commutes with TA. Just based on the commutation relations, you know the structure constants, and it's a consequence of the anti-symmetry of the structure constants. This is just like a line of algebra. That's what quadratic Casimir is. So representations are going to be labeled by the eigenvalues of this, and it commutes with all of them. Which means that you could basically treat it in your representation as an identity operator with a constant. Now, what is that constant? That's another parameter in SU2 or SU in the group. I'm sorry, I think I call it C2, sometimes I call it T2, right? So we determined that this guy is proportional to identity, but what is the coefficient of it? We call it T2 of R. This is different from T of R we just found, but intimately related. How are they related? How do you see the relation? We'll take the trace of both sides, right? Good. What is the trace of identity? It's N if you're in the fundamental representation. C2 of R. What is this? What is this trace? This is T of R, right? Where is the range of A? Huh? Dimension of the group. For SU2 is 3, right? So N times N minus 1 over 2. No, N times N minus 1. N times N plus 1 over 2. Yeah. Anyway, you can do that. Yeah. So they are related. Okay. So you could calculate them. Here I've calculated them for you. For SUN, this guy in the fundamental representation is N squared minus 1 over 2N. So that here, there you go. That's your answer. What is that for SU2? 3 over 4. Is that familiar? Yeah, J squared is 3 over 4 identity in an irreducible representation of SU2. In the adjoint representation of SUN, these two guys are equal and equal to N. Show that. This is pretty much all you need to have in mind, right? So if you're dealing with in the fundamental representation, right? T of N is, did I not say this? Okay, T of n, I think I dropped it. It's actually half. Fundamental representation. I gave you the example for SU2. It's always half. And then T of G for SUN is no, sorry. T2 of n, let's do the first two fundamental, is n squared minus 1 over n.
Correct.
2n. Okay. For adjoint representation, T of G is equal to T2 of G equal to n. This is all the numbers you need to know. Right? Adjoint and the fundamental. But do keep them in mind, because when we get to standard model, we have to constantly use them. Every calculation, these come up. Can you see why they come up though? Because all the physical stuff that they calculate at the end of the day are not going to be matrices. Matrices are not invariant. They're going to be traces. So you're going to be repeatedly taking traces of these generators. All right. With that said, here is TR. Now I don't need to explain what TR is. And whatever your representation is, it's this guy. Right? So if you're in the fundamental, it's just minus 1 over 4. If you're in the adjoint, it's going to be minus, adjoint of SUN is going to be minus 1 over, sorry, it's going to be minus 4. Oh, ha ha ha. This is 2. Wait a second. No, it's correct. This is correct. This is for non-abelian. What is T of R for the trivial representation? Zero. So this, as written, cannot be viewed as an answer for the, as a Lagrangian for the abelian case as well. This is purely angles. This is non-abelian. Okay. Is it clear why 0? Because the group representations are one-dimensional, so the Lie algebra is trivial. The matrices are 0. There's just one matrix. All right. So here it is. Minus 1 over 4 TR and the trace of R of the field strengths, non-abelian field strength. So let's expand this. If you expand this, first of all, you could write this down explicitly. Well, forget about this TR for now. You could write this down explicitly at trace as sum over k's. Is it clear what k's these are? Field strength is a matrix. And right? So you could expand it in the elements of the generators. And that's what it is. Now, F mu nu of K is del mu of A mu minus del mu of A mu plus this term. This is the, I called it F earlier. Right? This is self-interaction. Yeah.
Why is it so that last term sometimes written like this? Like that. Just the commutator.
You could, yeah, that's also a possible. Well, write it down. Write it down. What are those A mu's and A mu's? It's a cool one. Okay. What are those A mu's and A mu's? They're matrices. These are all non-abelian statements. That's not a very nice way of writing it because it doesn't connect with the abelian case nicely. All right. So the Lagrangian is no longer quadratic. Therefore, you have self-interactions. In SU2, there are 3 degrees of freedom. These are going to become the W and Z bosons, W plus minus and Z bosons, 3 degrees of freedom. SU3, how many degrees of freedom do you have? 8. So you have 8 gluons. They do self-interact. All right, so in summary, I'm doing well on time. Okay. To define non-abelian gauge theory, we define a covariant derivative. Here it is. So it's del mu is matrix valued. Let's take the matter to be in fundamental representation so that these guys are adjoint. This is what they look like. And they transform as Lorentz vectors, but as matrices in the internal degrees of freedom. Non-abelian field strength is written this way, right? And the Yang-Mills action is this. TR is the thing that comes out of the, I already now here switched to lambda. So anyway, now we can actually start this lecture because this is what I was hoping to go over last time. The question is, are there any, actually, that's a question. Are there any questions? What we're gonna do in the remainder of this lecture, and probably some of it will be done in the next lecture, is to talk about where does the covariant derivative come from? I'll give you a very physical geometric picture that should resonate with all that you've seen up until now. And then I'll explain what the non-local observables are. I've been talking about them for so long. What are they? And then in the geometric picture, it's actually, and then how do gauge theories come about? We saw how scalar field theory and vector models come about, right? So how does scalar field theory come about from a lattice, the continuum limit? You have the spin degree of freedom, the spin degree of freedom, and then once you coarse grain, it becomes a real variable, right? It's just it's slowly varying. It's a phase of that. The phase of it becomes a scalar field. I'll explain how these guys come about. It's very natural to land on a gauge theory starting from a lattice model if you do one extra thing. Do you know actually? Does anyone know? What's the extra ingredient that I have to add to my lattice models to get gauge theories in the infrared? You could do in one shot gauge theories and higher form symmetries. So what is a lattice? A lattice, let's say 1D lattice. What is it made out of? Lattice is generally a graph, right? It has a bunch of edges and a bunch of links. The links are organized in a very, very nice way, right? Connecting nearest neighbors. Where do you put the degrees of freedom in Ising model? Well, all the models we've been putting degrees of freedom on the vertices, right? That's going to be the charged matter, right? To do gauge theory, what you need to do is you have to put degrees of freedom on the edges. Charged matter sits on the vertices, and the edges make them talk. Putting degrees of freedom on vertices are called zero cells. They're zero dimensional. That's a zero, gives you zero form symmetry. If you put degrees of freedom on edges, they're one dimensional. You naturally land on one form symmetries. I'm oversimplifying, depends on your Hamiltonian, a whole bunch of things. You have to have the continuum limit. Given the continuum limit, if you have that, then you land on one form symmetries. So what's the two form symmetry?
Yes.
You put degrees of freedom on faces, right? Two dimensional things. Imagine a higher dimensional graph. You have higher dimensional surfaces. You put degrees of freedom on those, and it's natural to get the higher form symmetries. That's what higher form symmetries are. Torque code is an example of one form symmetry, degrees of freedom on a placket. So it's a gauge theory. What's the gauge group? Z2. Actually, I'll go over that. Well, not. I'll just give an example of Z2 gauge theory. I won't write down the Hamiltonian. All right. So now we're gonna do geometry of gauge theory. Actually, let me go on the board because I think I will probably have to remind you of that, guys, a little bit. So what is a gauge theory? What is a quantum field theory? Quantum field theory is, what's a quantum field?
From
It's a map from some space-time, some manifold, initial manifold, to a
targets.
target space. I'm calling X. Now, what's the scalar? What's the X target space in scalar field theory? Real scalar. R. In ON model, what was this? It was Rn. In nonlinear sigma model, we took it to be Sn. Right? Rn, Sn, all of these guys are Lie groups. Right? So you could view this as a map that at each point sits a group manifold, sits a group manifold. Yeah.
Why aren't these classical fields? You said it's
It's a classical field. Well, put it inside the path and go. So at each point, let's say you could think of it as a say Sn. Imagine Sn or U1 if you wish, but Sn is nicer. Sun. And at each point, the field is a vector, right? On this. So that is what the field at this point X is, and then the field at point Y is another vector. What is the kinetic term in the action? What's the kinetic term? Tell me what the expression for the kinetic term. Del mu of phi, del mu of phi. So you must define derivative. Now, if phi is a scalar, how do you define, what is the derivative? It's the value here minus the value here, right? Divided by the distance, taking the distance, go away. But if these are vectors living on some x, how do you compare? How do you say this point is the same point as that? Connection. You need a rule that tells you that this point is this point. These two are the same. And as you go from here to here, it went from here to here. Now it's moved this much. Right? Notice that that doesn't quite come up if your field is just a real scalar. So what do you need? Let's say G is S1, right? So phi A is just an angle on S1. At each point in space, you have a base manifold. So now what I'm doing is I'm imagining both M and X at the same time. This is called a base. This is called a fiber. The whole thing is called a fiber bond. What it is just locally, when I draw this picture, locally your manifold is M times X, right? Locally. This is called base, this is called fiber. All right, a group transformation at each point is a rotation. It moves around this point, right? And these are supposed to be redundancies. So if you have a vector, let's say if this is a really cool example. Say your space time is one-dimensional, and at each point you have a U1 gauge field, right? So this is your U1. Forget about space-time. Your base manifold is a line, right? So because rotations at each point, so now what is a field configuration? A field configuration is, so now we could view this as a cylinder. A field configuration is just something like this, right?
What do you mean something like this? Like
Theta of X. Something like that. This here is here, then here, and then here. Such a thing is called a section. Okay, so a field configuration is a section. You're with me? Now, if I say rotations are gauge, I can use rotations, gauge transformations to make every section trivial. Theta of x equal to 0. Right?
Wait, can you precisely define what a section is?
So it's this is a section. If your field is an angle on S1, theta of x is a section. Right? Now, if I say rotations around this are gauge transformations, and I'm free to do gauge transformation as I wish at every point, I can trivialize this section. This is called a trivial section. Yeah, local yeah, this is exactly. Could there ever be an obstruction to this? Can I trivialize every section?
It depends on the group.
Give me an example.
If your group has a more complex structure than just a circle, then you can go longer. Like, if the Christoffel symbol isn't trivial.
So, all right. I'm gonna draw this picture in a discrete way. Okay. Imagine your M is a circle. Good. So what you have is a circle, and at each point you have a circle again. So it's a torus, right? I'm gonna physically draw this as there is a vector sitting at each point. So it's like a Heisenberg model. Right? A Heisenberg model that looks like, I don't know, does something like this, whatever. Such a thing, I can always trivialize. However, what if it's twisted? If it does a twist, there's a topological obstruction. That section could not be made trivial. This is precisely what happens in space-time. There is M. In space-time, consider a loop, right? And at each point, say you have U1 gauge theory. At each point, we're just going to focus on this loop. At each point, you have a U1 gauge theory. So there's a circle at every point. If the field configuration of the gauge field, as it goes around this, is twisted and goes around, it's like a Mobius, it goes around once and comes back. It has a topological obstruction that could not be trivialized. It's like a Mobius strip. You can at every point you could point them, you could try to make all of them in the same direction, but as you go around, it's impossible. It's a topological obstruction. So gauge theories, even though locally you could trivialize, there are local gauge transformations. Local transformations. U of x locally is unphysical. In a non-local way, there are degrees of freedom that corresponds to these topologically non-trivial excitations. They're completely invisible if you didn't know about U of x. This has nothing to do, at the moment, I haven't told you how it's related to other things you know. Right?
Wait, so the topological obstruction in that case comes from the way the loop is constructed in space-time or from the group that you have embedded?
It comes from, we're focusing, it depends on both the fact that I picked a loop and a group. Is quantified by the fundamental group of the group. This, right? If you know what that is. And that's always relevant for gauge theory. For gauge theory, there are degrees of freedom, non-local degrees of freedom are associated with loops. They're one-dimensional things. In gauge theory, that's always the case. Right? Higher form symmetries, you would try to look for higher dimensional objects, right? And try to associate non-trivial, topological non-trivial things to those. So higher dimensional objects means SNs. S1 is trivial. Well, if you do know about fundamental groups and homotopy, S1 or the one form symmetry is the only case where you could have non-abelian groups. When you go to higher form symmetries, they become all abelian. All right. Okay. I'm jumping it on myself. So, all right, is the idea clear? Now we're going to go step by step and work through this. First, by the virtue of the fact that we want to define a derivative, we must have a connection. Right? What is a connection? Well, what is derivative? You have a manifold and you're moving in some n mu direction. N mu del mu of phi is defined to be limit of epsilon going to 0, 1 over epsilon of this. So to be able to define derivative, you must have a way of comparing, adding, and subtracting phi of x and phi of x prime. Said differently, you must have a way of transporting phi of x to x prime. Now, when you transport, it means that you haven't changed it. That's what it means. Transport, parallel transport, it means that, what does it mean to say this point is the same as this point? Right, that's the rule. That defines for you parallel transform, that defines for you connection. So if phi is a vector, to transport a vector from phi of x to another point, you need to multiply it by a function of from x to y by function of y and x. This is a non-local object. It's a matrix, right? That's the only meaning of saying that this is what a connection is. It will tell you what it means to say this point is the same as that point on the fiber, on the fiber, right? Now, if you do take a derivative of this, what you obtain is a covariant derivative. What's the origin of covariant derivative is this. There is no when you're dealing with matrices, there is no meaningful way of saying that I only take the derivative of the matrix. You have to have a rule of comparing two matrices at different positions. And in general, there is some W of y and x that sits in the middle. If you expand W of y and x for nearby points, this is an operator that lives on a line. It's not a local thing. If you expand this for points that are on top of each other's identity to the first order, what is it? It's the gauge field. So a gauge field is a choice of connection. And that's what the origin of covariant derivative is. If you thought you knew what you were doing when you wrote del mu of some matrix of x, it would be incorrect. This assumes the only way to define this object is to assume a connection. A connection means gauge field. So what is well defined is not really this. That's well defined. That's a particular choice of connection. Now it's easy to see that the covariant derivative transforms covariantly. Think about what that means. Now, a covariant derivative transforms covariantly, as it should. I talked about parallel transport. What does parallel transport mean? Parallel transport means that, what does it mean for the value of the field to have zero covariant derivative, right? You pick a connection, that tells you what it means for the field to have zero covariant derivative. That's what parallel transport is. At each point, you move in a particular direction with zero covariant derivative. Of course, it depends on the connection. Now, all along, now this might sound familiar from your study of general, if you've taken general relativity, this is of course intimately connected. What's the difference? Do you know what the connection is? In general relativity, what are the things that you're trying to parallel transport? They're vector fields in space-time. So this is M. A vector field in space-time belongs to the tangent bundle. So at every point, I was talking about a group sitting there. What you're dealing with is the tangent space, which is RD, say for M. So a vector field is something that lives on the fiber bundle that is locally RD times M. And of course, you have to have a way of defining what it means V mu at point X and V mu at point Y. And you need a connection. You need a covariance. Such a choice is a choice of parallel transforms, that's a choice of connection. Connections are, in this context, are called Christoffel symbols. Right? Now, if you do remember from general relativity, there's something interesting that happens with loops. As you go around the loop, as you parallel transport around the loop, you might not end up same place you started. For example, if your space is if this is my circle, right? This is a circle living on M. Now I'm going to parallel transport the naive way you would think, this way, and then this way, and then back this way. You end up not where you started. That captures curvature. What am I doing? By parallel transporting, I'm trying to make sure that I'm trying to make things trivial. I'm trying to make my gauge field trivial. But there's a topological obstruction to that. What is that? Curvature. Now, very good. What does it mean? So for the same reason, so gravity is exactly gauge theory, modulo some subtleties. So if you want to know what is the failure of if you parallel transport a tiny little loop and come back, one simple way of doing it is to say, well, when you parallel transport infinitesimally, what are you doing? You're applying d mu. So parallel transport d mu, and then this way d mu. Now back minus d nu d mu. What is this? This is just d mu. This is a curvature. So what the field strength was, it was actually capturing curvature.
So the field strength is like the equivalent of the Riemann tensor?
What's the commutator? What is the commutator of this in general relativity? Riemann. Yeah. That's curvature. Curvature tensor. It's a two tensor if you know differential geometry. When you parallel transport and not a field to come back, it's due to curvature and it's holonomy. Right? It's a topological thing. Same thing with curvature. Now think of QED. Take a loop, right? What is curvature in QED? In electromagnetism? It's F mu nu, right? F mu nu is what? Electric and magnetic field. Take a loop and imagine there is a magnetic field going through it. Good. Now, what do you know from Maxwell equations? That if you integrate gauge potential around this loop, it will be non-zero. So even though you call it gauge potential, meaning that at every point, so this is U1 at every point you could trivialize it. But because of curvature, there's an obstruction. This curvature is a topological obstruction to trivialize this. Now, why do I call this? So why do I call this non-locality? Can you tell what non-locality is? Why is it non-local?
It's local, you can trivialize it. But...
Because the value, so exactly, if this were local, it could only, like when you integrate a mu around this loop, a mu dx mu, at every point, you could try to trivialize this, but it depends on something that's not along the path you're integrating. The answer to this depends on what goes through the loop. Right? That's non-locality. That's the very meaning of non-locality, that you're integrating something on a line and it ends up depending on something outside. This is what the non-locality is. So gauge theory has, in addition to electric and magnetic field, which are F mu nu, curvature, it also has these loop non-local degrees of freedom.
How are they observed experimentally?
We'll get there. Follow the next lecture. They're called Wilson loops. Does anyone know how are they observed?
I don't know.
Are Yeah.
What's I don't understand what the curvature is here.
it's curvature is an abstract thing. Curvature, and it's not curvature in the language of space-time. It's just a commutator of the covariant derivative. All right. Okay, so let's see how far I want to go. I think I can do this as well. So now we just said all of this, right? We said that when we go from x to y, what we need is something that looks like W of x and y. W of y and x, which is a matrix. That is what a Wilson line is. We'll see that in a second. In the continuum limit, it will become. So first thing to notice is that this object, whatever the hell it is, it transforms like this. It transforms in the adjoint representation. But u of x on one end and u dagger of y on the other end. If it's going from x to y, its transformation on the it transforms with u of x on this side and u of y on that side. Of course, it was designed like that, right? So what does it mean? It means that this, if you consider phi of x, now this is A, W of x, y. This is, I don't want to do matrix multiplication. A and B, phi of B of y. This is gauge invariant. Can you see that? Under gauge transformation, this transforms like a u of y. This transforms like u dagger of x. This guy transforms like u of x here and u of y there. It's designed to do that. What is the interpretation of this? It's a Wilson line with two opposite charges sitting on the other on the endpoints. Two charge matter on the endpoints. If I don't want to deal with charge matter, how do I make this gauge invariant? Turn it into a loop. Okay. So I think I'm gonna skip this. In the non-abelian case, I think this is a Wilson line. So what you do is you take the Wilson line and expand it in small epsilon, and you get the connection, right? And it transforms in this following way. Good, you're with me? So it's the object that goes from here to here. Now, here is, I think, I'm gonna try to do this slide and then stop. What W of yx does for you is parallel transport along a path. All right. So let's do the following. Let's take phi and parallel transform from x to y. What does that look like? That's like integrating along this path of del mu of phi. Right? Now, because we're parallel transporting, del mu of phi could be written as a mu of phi. Right? This is covariant derivative. It's del mu plus I e a mu. So if the covariant derivative is 0, parallel transport. This is how it's done. Therefore, it basically phi of y is basically phi of x plus ig, this operator acting on phi of z. This operator is the Wilson loop. So I leave it to you guys to figure out that actually the full operation, if you have to solve a differential equation, phi of z, this y, w of y and x, is not just this, it's exponentiated, path ordered exponentiation of a mu dz. That's what the object is. So we produce these few lines of algebra, and I think I'll stop here. All right, so I'm just gonna summarize. So we didn't make it up to the end, but what is gauge theory? Gauge theory is a theory where you have a bunch of degrees of freedom that are local. In U1 gauge theory, electromagnetism is EMB, right? You have these local degrees of freedom, and then what you have is that on top of them, you have a bunch of non-local degrees of freedom. They're Wilson loops. This is the description that we've had. When you insist on a local description, it comes at the cost of introducing this fictional degree of freedom called a mu that could be locally trivialized, because that's unphysical, that's a gauge transformation. However, there are topological obstructions to trivialization of this every time there is curvature associated with this connection. Right? Curvature is the field strength. Now, an interesting thing that you learn is, think about this. I'm gonna leave you guys with in non-abelian gauge theory, Wilson loops are the local degrees of gauge invariant degrees of freedom. What other degrees of freedom do you have? Non-abelian gauge theory. Because the F mu nu is no longer gauge invariant.
That's right.
Well, think about it. All right. Are there any questions? I didn't get answer as I was hoping to, but anyway. I'll do a little bit of lattice gauge theory next time. So where I'm going to go with this next time is I'm going to tell you how you can get non-abelian gauge theory and the action I told you about, the Yang-Mills action, by starting with lattice and putting degrees of matrices on edges. This line, every line, think of this manifold and discretize it, make it a lattice, right? So a Wilson line is like you associate a tiny element here. All right. Are there any questions?
Are we allowed to say that F mu is the Riemann tensor of the manifold?
There's no meaning. Sorry. The Riemann tensor of the manifold